let's start rather. So yeah, right. So welcome to the webinar on regression in the kind of broad sense. So what I'll cover today, as I said, probably it's going to be a bit tight for time, I think, because there's kind of quite a lot I've tried to cram in, but even so, saying that, it's still very much surface level sort of stuff. But I wanted to start with going over quantitative research questions, so the type of questions that we can address with quantitative research, because that really kind of dictates a lot of how you think about how you approach your analyses. And then kind of the very sort of basic setup with a regression model, the kind of key components, with a focus on generalized linear models, which we'll come to. A bit about choosing suitable models, so in terms of thinking about what your variables are, and then a bit about kind of some cautions around common but problematic approaches. And then the final kind of long section would be on interpreting common model results, so different types of regression models. What do the results actually mean? How can you interpret them usefully? So I'm not sure how far we'll get through all that, but obviously, as I said in the email, I will make available after the session and in the coming days and maybe weeks, depending on how quickly things get done, additional resources. So, links to existing materials. We've got some good books and things like that, and there's lots of stuff online. And what I'd be aiming to do is produce code to run the models on example data in R and in Stata, because I know a lot of, particularly the Nigerian team, use Stata, so that you can then, kind of run through some examples yourselves in the software and see how you interpret the results, and also, kind of the other bits and pieces that you need to do as part of that modeling process. Okay, so in terms of quantitative research, hopefully none of this is too unfamiliar, and stuff we've talked about before. So there are three main types of quantitative research question that you can address. So there's descriptive questions, causal questions, which kind of the broad field of trying to answer causal questions is referred to as causal inference, or sometimes counterfactual prediction. And then the third main type or task of quantitative research question is around prediction. But as I say here, that's not really applicable generally for our research. I've never been involved in a study yet where we've made use of prediction, so I'm not going to focus on that at all. I'm just going to primarily focus on the descriptive side of things, and sort of touch a bit on the causal inference side of things. And that's just a reference that kind of describes this framework. So description, again, I won't spend too long on this. Hopefully that's kind of fairly, nothing new to anyone. So there are, different types of descriptive questions that we can look at. We can look at, what's like the level of some outcome, what are the differences in levels of an outcome, whether that's, like the prevalence of an outcome, or like here, my example would be, how does the average level of readiness of diabetes services differ between different types of services, different types of facilities? Trends or relationships, again, that might be what's the relationship between number of providers per facility, and how does the average service level, average percentage of readiness change. So descriptive questions, really, really useful for understanding like the scale of a problem, the location of a problem, variability. So, like we looked at there, how it differs between different groups. So really, really useful, and often I think underappreciated to some extent. But the key I guess, point here is that we're just talking about surface level relationships. So we're not assuming any causal relationship. So we're not saying, just because this relationship exists, that shows that, one thing causes the outcome to change. It's just we're describing what things look like on the surface level. So great for planning, great for understanding problems, great for planning, that kind of thing. I just wanted to touch briefly on an issue that I sometimes find people get a bit confused about. So when we're talking about description here in terms of quantitative studies, trying to describe things, we're talking about what you might call inferential description or descriptive inference. I find that there's not really kind of commonly accepted terms for this, but the confusion comes by the fact that descriptive statistics are just relating to the sample at hand, whereas normally in a quantitative study, our goal is to generalize our results to a target population. We're not just interested in the sample, and for that we need our measures of inference, which normally would be confidence intervals. P-values are another type of inferential measure, but without going into kind of too many nitty-gritty details, the kind of modern advice, the modern approach is, to focus on confidence intervals, because your p-values are directly related to the confidence intervals and they don't add anything and they're much less informative. So I'm just going to skip through that a bit. So last bit on description I wanted to say, so as I say, it's often, I think, undervalued and underappreciated. And there's just a couple of references here that I've got. One on the need to revitalize descriptive epidemiology, which is a really good paper about, by some very prominent authors who are actually really prominent in the causal inference world. But they're actually calling for, much more emphasis and rigor and attention to be paid to descriptive epidemiology, which is sort of often marginalized. And there's a lot of really useful and important excuse me, value in descriptive studies. And then this other paper, a framework for descriptive epidemiology. This is kind of similar to a lot of the frameworks, checklist templates that we've got for other types of studies, like Consort for trials, Strobe for observational studies, etc., etc. So it's a really nice framework for if you're going to do a descriptive study, all the things to think about, all the things to report in the paper. Can I just check, can everyone hear me okay still? I just wouldn't want to be talking into a void, and because I can't see any text, any chat.
Yes, we can hear you, Joe.
Okay, great. So very briefly, causal inference or counterfactual prediction. This is where we're explicitly trying to understand causal relationships. So where we want to understand how does one thing directly influence another thing. And kind of broadly speaking, it requires a lot more often, to do it kind of well, to do it rigorously, typically requires more complicated and costly study designs, so typically longitudinal designs, and much stronger assumptions than for simple description. So not going to go into any details here because the focus is on regression, but the kind of studies we're thinking about, things like RCTs, interrupted time series, difference in differences. And again, we're focusing on our inferential measures to generalize the relationships that we're estimating to some target population that we've got in mind that we've sampled from. And again, I'll provide some materials relating to that. Okay, so come back now to regression. So regression is, in the broad sense, a kind of very large range of statistical models. So there are absolutely tons of regression models. If you Google regression and go on the Wikipedia page, there's just a massive range of models, most of which I've never come in contact with. So it's a very large sort of field. And regression models are very flexible, very general. So they're, you can use them for description, you can use them for causal inference, you can use them for prediction. But one key thing to bear in mind, which again, I think maybe if you're just kind of starting out in this sort of world, really key thing to bear in mind is, these models just give you statistical correlations or statistical associations. So they just give you a measure of how correlated your variables are. Whether that has any, how you interpret that in kind of meaningful real world terms depends very much on the whole kind of range of things from the start of the the research question you're considering, the study design, the variables that you've measured, how closely they relate to the real world phenomena that you're interested in, all the kind of sources of bias that might be operating in the study, etc., etc. So basically, just bear in mind, if you a regression model is just a model, it's just a measure of correlations, really, and how we make use of those and how we meaningfully interpret them in real world terms depends on a much larger range of considerations. And just to kind of reiterate, I think regression is often an underappreciated tool for description. Descriptive studies are often, I think, more basic and less kind of rich and powerful than they could be. And regression models are one way that you can get much more rich and kind of useful results from those studies. Okay, so we're going to focus on generalized linear models plus at least one other related model. So just a little bit about terminology. Sometimes you might see the term general linear model as opposed to generalized linear model. And so general linear model is kind of the more, I guess you might say, kind of specific descriptive term for a linear regression or an ANOVA type analysis. So that would be a general linear model, whereas a generalized linear model is kind of extending the general linear model beyond the simple, or not necessarily the simple, but beyond the linear regression approach where we assume normal errors, and we'll come back to that in a moment. So this would be things like logistic regression and so on. So what's the broad aim with a regression analysis? So broadly speaking, it is to model the relationship between one outcome variable, which, again, a bit of terminology you might see referred to as a dependent variable or as a response variable. I tend to use the term outcome variable, but other people prefer different terms. I don't think there's any kind of particular pros or cons. So we're looking at the relationship between one outcome variable and one or more independent variables. And again, you might see those referred to as covariates or explanatory variables or predictors. I think sometimes I use the term independent variables or covariates, but I think explanatory variables or predictors are a bit more loaded in terms of the terminology, because that implies some sort of maybe causal relationship, which you're not necessarily even explicitly trying to measure. So I tend to stick with the slightly more neutral independent variables or covariate terms, but just so you kind of touch on those which you might see. And one more bit of terminology. Again, it's not sort of super critical, but there's a tendency to call what is actually multiple regression, where you've got, let's say, 2, 3, 4, 5, however many independent variables and one outcome, to call that multivariate regression. But strictly speaking, that's not correct. Multivariate regression would be regression where you have more than one outcome variable. And those type of models do exist, but they're, I think, fairly rarely used. I've certainly never encountered any. And how you kind of go about interpreting them, I think, would probably be a bit of a nightmare. So yeah, just be aware. The correct term is multiple regression when we've got more than one independent variable, not multivariate regression, unless you really do have more than one outcome variable. So back to GLMs. which is the synonym for generalized linear models. So this is the broad kind of family of models that we're going to be thinking about. And so there are three components to a GLM, and they're the same actually for most, regression models, for if you kind of go beyond that. So we've got a random component, which is the assumed probability distribution. So this is the assumption that we make about how the unexplained variation in the data, the kind of pattern that it follows. And what we do is, with the model, we try to model the mean of the assumed probability distribution. And then the probability distribution, assuming it's correct, then allows us to describe the unexplained variation, which we're not able to explain in terms of the data that we've collected, so in terms of the independent variables. And that's critical because that then allows us to make inferences. So assuming that we've chosen kind of a correct probability distribution, that allows us to then and assuming there's kind of no other sources of bias, which is never really going to be true, it allows us to then make our inferences to the wider population. And so with GLMs, with generalized linear models, the probability distributions all come from a kind of family of probability distributions known as the exponential family. So we won't go into any details about what that means, but this is but in the kind of the commonality to all of these probability distributions is that they all have a parameter, which is which is this parameter here, which is the Greek letter mu, or we refer to the parameter with the Greek letter mu, and this is known as the mean parameter. And this represents the expected value that you would get over repeated samples. So essentially, if you were to repeatedly sample that outcome, assuming it came from the probability distribution that you've made an assumption about, over many and at the limit over an infinite number of repeated samples, you would get you would expect that the average value that you would get would be this mu. It would be the expected mean value. So for like a normal distribution, which I'm sure you've probably all come across before, the mean parameter represents the expected value, which you can kind of think of as analogous to the sample mean, like where we add up all the outcome values and we divide by the number of them. So it gives us a measure of like the typical value that we'd expect. So it's not necessarily a value that's going to be in our data set, or that you might ever measure, given that a continuous variable, you can measure it down to any level of precision, but it's a measure of the typical expected value, or the center of the distribution. Another probability distribution that is very commonly used and we'll come back to in the context of logistic regression would be the Bernoulli distribution, or more generally the binomial distribution. And here the mean parameter mu is the expected probability of success. So it's we'll come back to that before I kind of define it further. And then another final example will be Poisson distribution, which we use for modeling counts or rates. And here the mean parameter mu measures or represents the expected rate at which events occur. So this mean parameter mu is kind of the key thing that we're going to be trying to model. So we want to understand how our independent variables affect the expected outcome under the distribution that we've chosen. Oh, and sorry, I should have said at the start, obviously any questions at any point, just come on the microphone and let me know, because I can't really have the chat up at the same time. So please just interrupt and let me know. Okay, so that first component of generalized linear models is the random component. The second key component is what we call the systematic component. And this is also referred to more commonly as the linear predictor. And so this is what explains or predicts the mean of the assumed distribution that we've chosen. So this is where our independent variables come in. So the linear predictor looks like this equation here. So we've got our x's are our independent variables, and obviously we might have one, or we might have two or more. So we can have any number of independent variables, and then the betas are the weights or the coefficients, and these basically represent how much each independent variable contributes to the expected mean. So broadly speaking, if you've got positive betas associated with a given independent variable, that represents that as the independent variable increases or is true for a categorical variable, and we'll come back to this in a bit more of a kind of concrete example, then the conditional mean of the assumed distribution is going to increase, and likewise vice versa. If you've got a negative beta value, then the conditional mean is going to increase as your independent variable gets higher or is true. Now, one thing to note is that this linear predictor is just a simple linear sum. So we've got each coefficient is multiplying the value of the independent variable, and then we're just summing it all up. So that linear predictor can range from any value, any negative value to any positive value. So that's its scale. So its scale is the real numbers from negative infinity to positive infinity. So that's a key thing just to bear in mind that we'll come back to in a moment. And then one more little bit of terminology. When we talk about a linear model, as we'll see later on, it doesn't necessarily mean that we're not modeling non-linear relationships. We can use linear models to model non-linear relationships, so kind of squiggly lines, curves, that kind of things. But the linear bit comes from the fact that it's linear in the parameters. So we mean that it's just a simple sum. So we'll come back to this, we've got the intercept, and then we've got our kind of first coefficient times our first independent variable plus our second coefficient times our second. So we're just multiplying the coefficients by the independent variables and adding them up. There's no, we're not kind of doing anything more fancy than that in terms of any other kind of more complicated operations. There's like no divisions or higher powers explicitly in the betas or anything like that. Okay, and then the third component of a GLM, or typically a regression model, is the link function. And this is what links our random part, where we've got the probability distribution, and the systematic part, or the linear predictor. So we represent this often as this like G of U. So we're saying G is just some transformation, so some mathematical operation that we're going to apply to our PDF. And I'll go over this just briefly now. If this is kind of not making much sense, don't worry about it. Just you can come back to it at a later date and kind of go into some other materials and kind of try and look at it from a bit more in depth. But I just wanted to go through these bits, so at least you've kind of had an exposure to these concepts, and then when we come to the interpretation of the models, hopefully it kind of makes a bit of sense about why we have to go about transforming some of the results that we get to make them meaningful. So this function ensures that the transform probability distribution it ensures that the probability distribution that you've chosen, it ensures that the mean parameter and the linear predictor are on the same scale. And there are lots of different possible links, but there's, for each PDF, each probability distribution, there is one natural or canonical link that's usually used, and we'll just we're not going to we're just, in the examples I use, we're just going to stick with those. So just to give you a kind of quick understanding or quick feel for why we need to make these transformations, with a normal probability distribution, so this is what we use with linear regression, the mean parameter mu is on the real number scale. So the mean parameter mu can vary from anything from negative infinity up to positive infinity. And if you remember, we said the linear predictor can also vary from negative infinity to positive infinity. So the two things are on the same scale, so we don't need any transformation. So in linear regression, the transformation is implicitly called an identity transformation, which basically just means we don't do any transformation. So that's nice and easy. But to give you an example where we kind of do need to make an explicit transformation, logistic regression, the probability distributional probability function that we use has a mean parameter which is the expected probability. And so obviously probability, can only be from 0 to 1. So now we've got a problem because our linear predictor is, can vary from anything from negative infinity to positive infinity. But the thing we're trying to predict, the expected probability, is on a 0 to 1 scale. So then we have to use an explicit link function. And in the typical logistic regression case, we use this thing called the logit or the log odds. And that takes the mean parameter from the 0 to 1 scale to the negative infinity to positive infinity scale. And then we're good to go. The linear predictor then is going to make, it's not then possible for linear predictor to predict values of the mean parameter that aren't possible. Okay. Very briefly, how do we go about fitting GLMs, which means how do we go about choosing the coefficients for the linear predictor? So those are the things that we're going to come back to and think about how we interpret them. So very briefly, we use this thing called maximum likelihood, which qualitatively in words, we maximize the likelihood of the data. So we've got our data, we've got our data that we've collected. That's kind of fixed. And what we do is we use some clever maths with the probability distribution that we've chosen and the model to maximize the likelihood of the data given a set of coefficients. So that this process finds the coefficients that make the data most likely given our assumed model. Again, don't worry too much about if that's kind of not making too much sense. You can come back to that at a later date. And, when it comes to interpreting the model, I think it's fair enough to say that that's, not necessarily too much of a kind of key consideration. Okay. So just then a little bit on key GLM or key regression model assumptions. So really the main critical assumptions are, first of all, independence of observations. So this is saying we're assuming that each observation in the data set is independent. So there's no correlation there between the two. Where this might break down would be, say, you are taking repeated measures within an individual. So maybe you're measuring observations within individuals over successive periods of time. So that would be in longitudinal data. Or maybe you have clustered observations. So maybe your observations come from sampling, health facilities or certain communities. And then, there's a good reason to believe that the observations, so maybe that's, patients or maybe it's community members, that the outcome that you're measuring is going to be more correlated within a facility. Individuals in that facility are going to have a correlation there. So your default kind of GLM regression model assumes the observations are independent. So obviously when that breaks down, when that's not true, then we have to think about how we address that. And I'm not going to cover that here because I don't think I have time. But certainly we can in kind of the example code, and follow-up materials, we can think about how you address that, because that's, generally speaking, it's very rare that you have independence of observations, because normally that would require a simple random sample, and that's rarely possible. The other kind of key assumption is that you've chosen a valid distribution, so a distribution that's correct for your data in your model. And that it correctly models the variance, so that the unexplained variation that isn't explained by your independent variables. And again, not going to kind of look at this any further now, but certainly checking the assumptions of your model, which often comes down to kind of plotting different plots of what are called residuals, is a really important part of the process. But we'll have to kind of look at that in the kind of follow-up materials. Okay, so that whole bit is obviously maybe quite technical. Let's think now, hopefully a bit more in a practical applied side of things. How do we actually go about choosing a suitable model for your study? So I mean, there are kind of lots of different considerations, but probably the most important one that you need to think about is, what is your outcome variable? What type of variable is it? What type of data is it that it measures, and what probability distribution then will best model it? And as I say here, in all the examples are just assuming what's called the canonical link, so kind of the default link. So we're not going to go into that in any more detail. Okay, so continuous outcomes. So this, you're probably fairly familiar with this. Typically the starting point would be linear regression. And so that would be using a normal or a Gaussian distribution. So sorry, when I say normal or Gaussian, I don't mean those things are two different things. This is just hopefully so that if you haven't come across these terms before, particularly Gaussian, so it's just, a bit clearer. So the normal distribution and the Gaussian distribution, they're the same thing. It's just different terms for the same thing. Gauss was, I think, one of the people who helped to define the distribution originally. So like in R, I'm not sure about Stata, but certainly in R, often when you are setting up a GLM with code, when you specify the distribution, R wants you to call it Gaussian rather than normal. So just to be aware, normal distribution or Gaussian distribution, which are the same thing, that would be what we would typically go to first for a continuous outcome. So that would be things like, biological characteristics. A lot of biological characteristics like blood pressure, blood glucose, they're often normally distributed, or at least approximately so. A lot of tools, psychometric tools like quality of life tools, those kind of things, they can often again be at least approximately quite nicely normally distributed, and so linear regression is a decent model for them. Common challenges with this type of modeling approach, things like when the assumptions break down, so when the distribution actually isn't non-normal, or when there's heteroscedasticity, which again I don't have time to go into detail here, but that would be when the variance isn't as you expect it to be. It isn't a constant variance. One distribution which you might not have come across before, which is well worth bearing in mind if you have an outcome which is continuous but is non-negative, so it can't be less than 0, and it might often be right skewed, is the gamma distribution. So that can be useful for those kind of outcomes. So things like costs. So I think the gamma distribution might be used sometimes, because I've not really used it myself often, but I think for costs it's quite useful, because a lot of any financial cost data, like the cost of services, it's going to be non-negative, and often it's going to be right skewed. So that's one that's worth bearing in mind for that. Okay, binary outcomes. So what if you've got a binary outcome? So it can only take on 2 possible values. Well, again, I'm sure you're probably all familiar with this. You can use logistic regression, which is a generalized linear model where we assume that the errors, the probability distribution, follows a Bernoulli distribution. Again, in the stats world, unfortunately, terminology can be like a bit of a headache. So the reason I've got binomial in brackets here is that often you might see the distribution for a binary outcome referred to as the binomial distribution. So like in R, when you specify a GLM for a binary outcome, so when you're setting up what is a logistic regression model, you tell it that the family, the probability distribution, is binomial. And that's not wrong. It's just that, strictly speaking, for a binary outcome, you're using a Bernoulli distribution, which is kind of a subset of the binomial distribution. It's like a kind of restricted version where the outcomes can only be one of two values. So yeah, two possible events. Basically, if you've got binary data, there's not too much that can go wrong in terms of whether you're making a correct decision about modeling it with a Bernoulli distribution. So that's normally kind of it should always be a good choice, really. True binomial outcomes. This is something that may or may not be familiar to you. So true binomial outcomes, again, we can use a logistic regression with a binomial distribution. The difference here is that our outcome is now no longer just a binary yes or no. It is the number of events occurring during a given number of independent trials. Trials is just the terminology that's used in kind of the stats world for it. So an example might be, say you've measured the number of required services present out of the number of required services per facility. So maybe you've got like a checklist, and there's like 10 required services for diabetes, and at each facility you measure how many of those services, how many of like the items are present. And that would be a true binomial distribution, because you'd have for each facility you'd have a certain number of events, which in this case would be the number of services that are present during the number of trials, which would be the number of required services. So that will be out of your your total that you're looking for. Or another example might be the number of NCD, the number of doctors that are trained to treat NCDs out of the number of doctors per facility. So the number of doctors per facility would be thought of as the number of trials, and the number of events would be how many of those are actually trained. So those would be true binomial outcomes. And when you're working with true binomial data, it does get a bit more, there's more room for problems to creep in, because you can have problems of non-independence, so where the trials aren't truly independent, and this thing called over-dispersion, which is kind of analogous to heteroscedasticity, but yeah, we won't go into the details. Count or rate outcomes. There are kind of three main approaches, three main distributions, or sort of modifications of distributions that are useful for that. So there's the Poisson, the quasi-Poisson, and the negative binomial. So counts always have a time or an area component, at least implicitly, which may be constant or it might vary. So for example, the number of stockouts per facility during January 2023. So say you measured across a large number of facilities how many stockouts of essential drugs they reported during January 2023. So there's kind of a constant time component there that's fixed, or maybe the time component varies. So maybe you're interested in the number of road traffic accidents per village. So you look at a number of villages and you measure the number of road traffic accidents that have occurred during a certain number of months in 2023. And maybe some of the villages measure, record road traffic accidents just during 1 month, and maybe some measure it during 2 months, some measure it during 3 months. So in this case, the time component would vary. So yeah, sometimes the time component is just kind of implicit, like when it's constant, it's often kind of not acknowledged. But if you're, the effort that you're making in your data in terms of how much time you've recorded you've used for each observation, or maybe the area component varies, then that is kind of a part of the outcome which you can account for in the model. Challenges, again, often the main ones come down to kind of problems with whether the variance is being correctly modeled. And yeah, we won't go into the details, but we can certainly look at those in kind of the offline follow-up side of things. Okay, last one that I wanted to look at before, I think then I will touch on a bit about choosing the models or choosing the variables, and then we can kind of look at some actual examples, would be multinomial outcomes. So multinomial outcomes, we use a multinomial distribution. And here, this is where each observation is one of three or more events. So, remember with logistic regression for binary outcomes, the observation, so the outcome, can only take, one of two events. Either it occurred or it didn't occur. And, maybe each observation is binary, or maybe each observation is the number of occurrences out of the total number of trials. But here, you've got three or more events that are distinct that can occur. So maybe our outcome might be primary care facility type, like is it private, is it public, is it NGO? So there are three possible outcomes. It can be, one of these three facilities, and they're mutually exclusive. Each outcome can only be one. You can't be kind of part private, part public. So we assume that, they're mutually exclusive. Multinomial outcomes or multinomial models, they can also be applied to ordinal outcomes. We're not going to go into the details of that again because it gets kind of quite complicated. So, I think if that's something that people want to look at a later date, we can certainly look at that. But you can use multinomial models for ordinal outcomes. It's not necessarily going to address the precise research question that you want, but it might, provide a way to do that. Common challenges, that's something that I need to look into a bit more, to be honest, because I've not got much experience using multinomial models, and there's not kind of as much useful information out there on that. But, as I say, if people wanted to look at using multinomial models, if that's, something that's going to be useful for a research question you've got, then, we can look at that. Okay. So model interpretation. So how do we actually kind of make use once we've run our model? And we will look through, so this, I'm just talking here in kind of the general sense. We will, I'm going to make sure that I kind of skip on it if we get a bit short on time so that we can actually look at some actual practical examples. But in the general sense, how do we, make sense of the models? How do we actually use them to tell us useful things? So there are two, I think there are two kind of broad approaches that can be very useful. So the most common one, by far the most common one, is to look at the model coefficients. So the model coefficients, which again, more terminology, sorry, you might also see them referred to as parameters or betas because of the typical notation, or weights. Regression weights is another one that you see, but it all means the same thing. I tend to use coefficients. So the coefficients give us the actual modeled relationships between the independent variables and the outcome. So broadly speaking, they tell us the association of each independent variable and the expected mean. So the positive or negative contribution of each independent variable to the expected mean. But remember, this might be on some kind of transform scale. Like in a logistic regression, it might be on the logit scale. And so we'll come back to kind of how we then have to, or we don't have to, but how we typically transform it, because on the logit scale, it's, pretty unintuitive and not very useful to us. Okay, so let's think a bit now about independent variables and the different types of independent variables, and therefore how they're kind of set up in the models. So depending on how you think about it, there are kind of 4 or 5 types of independent variables. We've got binary independent variables, we've got categorical nominal ones, and we've got categorical ordinal. Hopefully none of that's too unfamiliar. I'm kind of conscious of the time, so I don't want to spend too much time on this. And then we've got numerical scalar ones. So like we've got discrete variables, so that would be, counts, where the independent variable can only be a whole integer. So maybe like the count of the number of doctors per facility, it can only be 0, 1, 2, 3, etc. It can't be like 1.2. Or we've got numerical continuous, where the independent variable can be continuous. So maybe some kind of biomedical measure. And broadly speaking, although the kind of maths underlying it isn't actually really distinct, conceptually we can kind of think of modeling them in two ways. We model for categorical independent variables, we're modeling things in terms of differences. And for continuous or discrete independent variables, we're measuring the relationships as slopes or trends, you might call it. So just a quick note, with our linear predictor, you might have noticed the initial coefficient doesn't have a independent variable associated with it. And this is called the intercept, this coefficient. And this represents the expected mean of the outcome when all the other x's are set to 0. So in this little sum, if you imagine each of the x's are all set to 0, then obviously when we multiply any coefficient by 0, we get 0. So they kind of are all switched off. So then we're saying that the conditional mean of the outcome just equals our beta naught. So beta naught is then the way that the model fits it. It's then chosen as being the expected mean of the outcome when all the other x's are 0. And as I say, that may or may not have any useful interpretation depending on how we've set up the model. Then for numerical variables, whether that's a discrete variable or a continuous independent variable, our betas represent the slope, or what you might think of as the incremental difference. So it represents the positive or negative difference in the expected mean of the outcome as our independent variable increases by 1 unit. And we'll come back to, as I say, some practical examples to kind of hopefully clarify that if that's not, something that is already very familiar to you, may or may not be. Okay, so numerical variable, independent variables, thinking in terms of slopes or trends. Binary independent variables, we're thinking in terms of differences. So if it's a binary independent variable, ultimately the software will code it as a 1 or a 0. And this is known as dummy coding or reference coding. And then the coefficient just represents the difference in the expected mean of the outcome for being in category 1 minus being in category 2. So maybe, we've got males versus females, and males are coded 1, females are coded 0. The coefficient associated with sex will then tell us what the expected mean of the outcome is, the difference in the expected mean of the outcome for males minus females. And obviously, if you want that the other way around, you just switch the coding. That's fully under your control in how you set up the model in the software. What if we have a categorical independent variable where we've got more than 2 categories? So it's not binary, it's got 3, 4, 5, however many categories. Again, we're looking at differences. So it's very similar to the binary case, but now we've ultimately got more comparisons that we need to make. So again, in the software, your variable might be coded, with like labels, qualitative labels, but ultimately what the software will do is it will create n-1. So say you've got 3 category levels in your independent variable, it will create 2 dummy variables. So let's just look through what time we're on. Okay, let's just look through quickly how this might work for an independent variable where you've got location, and you've got 3 category levels. You've got your facilities are either in a rural area, an urban non-slum area, or an urban slum area. So again, it's this thing called dummy or reference coding, because we choose one category to be the reference, which, again, obviously you decide. And then every other category level is compared to it by these 2 additional dummy variables that get created. Okay, so just to see how this kind of works in the data set. So over here, we've got the observed category level. So we've got our independent variable for facility location, and it's either rural, urban non-slum, or urban slum. So we'll just pretend these are the first 3 observations in our data set. But, in practice, this is going to extend far down with lots of other observations. And And in our first row, this one highlighted in red, we can see that the expected mean of the outcome is just the intercept, just the beta naught coefficient, because our dummy coding is such that because this observation is rural, for urban non-slum, the dummy variable is set to 0, and for urban slum, the dummy variable is also set to 0. So in the linear predictor, those betas get multiplied by 0, so they just drop out, and you're just left with the beta 0, the intercept. And so the way that the model fits it is it means that this then, you're then left with the expected mean for the rural category. So in this case, the intercept does have a meaningful, like a useful interpretation. And then we can see, let's look at the second row. So now we've got an observation of a facility in urban slum. So now the linear predictor is the effect of the intercept, which is the expected mean for being in a rural, plus the difference that takes us to what we need for an expected mean for an observation in a non-slum area. So now our x1, our independent variable for being in non-slum is now switched on. It's a number 1, and our independent variable for being in a slum obviously is switched off because our observation is of a non-slum. So now we've got our intercept plus our effect of being in non-slum, and so now the beta 1, which we're interested in, that is now the kind of additional change in the mean, whether that's positive or negative, that we would need to add to the rural mean to get our expected mean for being an urban non-slum facility. Okay, right, let me just... Right, very briefly, what happens then when you've got lots of independent variables? Okay, so this is a common situation. I mean, it's the norm. You've done a study. Hopefully you've got a nice clear research question. You've got lots of independent variables. How do we then interpret the regression model? Well, if you kind of had multiple independent variables, then each of the betas, each of the coefficients is interpreted as before, so as the expected slope or the difference. But while assuming that all the other variables in the model are held constant. So it's what you might call an independent or an adjusted effect. So it's been adjusted for all the other associations in the model, and this should be the independent association. But as I said at the start, regression models just give you correlations, and similar to my kind of comment there about whether that's meaningful or not, it depends very much. Well, again, independent associations, whether that's meaningful or not, depends very much. So this is kind of a warning, or maybe not a warning, but just a be aware of the reality of the situation versus, I guess, what I would say is kind of overwhelmingly common practice. So this paper here, the table 2 fallacy, is a really well-cited paper that was kind of one of the first to really make the point that if you look in most observational studies, particularly a lot of papers that come from cross-sectional surveys, you will see often as the table 2, but the fact it's, whether it's table 2, table 3 is irrelevant. You will see often lots of tables of regression results where there is a whole load of independent variables, and the effect or the association of each of those variables with the outcome is presented and is interpreted in in the discussion, often in terms of being sort of independent associations. So this is a really, really common approach. As I say, you'll see it all over the place, but the problem is that from a kind of an interpretational perspective, particularly from a causal interpretational perspective, it's not really clear then what that big table of results actually means, if it's actually telling you anything of use. So the problem comes from the fact that and again, I don't want to spend too much time on this because it's a really big, complicated area, and I want to try and get to some of the regression interpretations. But the problem comes from the fact that depending on what variables, independent variables you include in your model, can have a big effect on what associations, what the associations actually mean. So very, very briefly, if you're trying to understand a causal effect, a causal relationship, there are lots of different kind of things that you either have to adjust for or not adjust for. And if you do those incorrectly, then the relationships actually, don't necessarily mean anything. They will be biased. So, hopefully you'll have come across confounding before. So when we're trying to estimate a relationship, let's say the relationship between alcohol and lung cancer, so alcohol is the independent variable, lung cancer is the outcome. What causal effect does alcohol have on lung cancer? To understand that, we need to adjust for any confounders. But if there are indirect causal paths, then we also need to not adjust for those if we want to get the direct effect. If we adjust for them, then that kind of changes things around a bit. There are also these things called colliders, where from the causal perspective, if the independent variable or the assumed cause causes some kind of third variable, which is also causally affected by the outcome, this is called a collider. If you adjust for a collider, so if you include a collider in an independent variable, then the association between your independent variable and the outcome, which you are presumably hoping is causal, or at least potentially causal, this can cause big bias. It can even flip the association around from positive to negative. And then kind of a related problem is this thing called M bias, where again we've got kind of we kind of open up biases in the associations that we're looking to measure by adjusting for these additional variables. So basically, you can't just basically chuck everything into one regression model and interpret all the independent variable coefficients as having some kind of clear, meaningful relationship with the outcome. Because doing that, you're just not clear whether you have correctly adjusted for if you're looking at each of those independent variables, each one, if you want it to have a kind of a meaningful relationship, you need to think through, have I adjusted for the confounders of that relationship? Have I not adjusted for any colliders or M bias variables? Have I adjusted or not adjusted for any mediation, depending on what I'm wanting? So, I appreciate this is kind of lots of different bits and pieces, but the broad message is this is kind of, it's very common in papers to see a big regression model with all the independent variables, and then all of them discussed in the discussion as being independent associations. And that's not wrong really, in the sense that, yes, they are independent associations, but the problem is that their kind of real world interpretation is pretty murky. There's not really any clear cut, are you saying that they are possible causal effects? I mean, if they are, then you haven't necessarily, adjusted correctly for confounders. You haven't necessarily not adjusted for colliders. Are you just saying that they're kind of, correlations, and you're not interpreting them in any causal way? Well, if you're not, then why are you not just doing it descriptively? Why are you then adjusting for kind of various other variables? If you're adjusting for various other variables, that's normally because you're trying to isolate a causal effect. So this is kind of this is kind of a problem that I only really came across a couple of years ago, and I haven't really had that much. It's it's something like the table 2 kind of approach is definitely something that I've done plenty of times before, and as I say, it's the most common approach in the literature. But there's more and more of a push to kind of be explicit in your approaches, whether you're being explicitly descriptive or explicitly causal, and being aware of all these kind of really technically challenging problems. So I guess kind of some initial advice I would say would be, and this would be focusing on on survey papers. Obviously, if you're working in from the perspective of you're explicitly trying to understand a causal relationship, and you've got a study design which would typically be recognized as being valid for that, like a difference in difference design, or an interrupted time series, or a trial, then obviously you think through what are your likely confounders, what are your likely colliders, and then you decide whether to adjust or not for them. And we can think through that as and when it comes up. But in the kind of typical case where you've got like cross-sectional survey papers, so you've got like a cross-sectional study, and what are you kind of wanting to do there? So I would say the things to think about would be to have very specific, explicit, clear research questions. So if you're thinking about description, what are the specific differences or trends that you want to describe, and why? There's not there's lots and lots you can do just purely descriptively, that can be very useful. Or possibly think about targeting potential causal effects, in which case you'd have to kind of really, if you want to do that properly, the things to think about first of all would be to kind of think through using these what are called DAGs, directed acyclic graphs, to think through what are the likely confounders, what are the likely colliders, and then using that to help you decide whether to adjust or not. But that's that's a lot of extra effort for a study where typically in a cross-sectional study, no one most people are going to they're going to be fairly skeptical about whether you can actually interpret those things causally, because obviously the main problem there is that you've not got longitudinal data, so that any possible causes don't necessarily precede the outcome. So that's kind of the big weakness, and why we typically use longitudinal studies for doing causal inference. Okay, maybe that's just a bit I'm not sure what the term would be, but ultimately, if you feel the need to do a traditional table too, as I say, no one's going to stop you. So I guess what I'm saying is, be aware of these issues, and be aware of the fact that if you have a regression model and you kind of chuck in a load of independent variables, whether each of those variables has much of a kind of clearly defined interpretation is, I guess, open to question. But as I say, no one's going to stop you doing that. It's still an extremely prevalent practice. Okay. Right. Time is obviously getting tight, so let's try and skip on to some practical interpretations. So I just want to touch on the other main interpretational approach that you can use for a regression model is this thing called marginal effects. And these can be really useful to aid interpretation, because often the coefficients, particularly in more complicated models, can get really messy and really unintuitive. And it's just a nightmare, frankly, to kind of work out what the model is actually telling you. But marginal effects can make your life a lot easier. And these basically use the linear predictor to make predictions from the model. And you then use those predictions, or the software uses those predictions to then do useful things like estimating adjusted comparisons between groups. And it does this on useful scales. So like you can get differences in probabilities rather than odds ratios or logits, which we'll come back to, but is really not necessarily very intuitive. Or for slopes, you can get average adjusted slopes, and again on useful scales. Okay. Right, I'm going to skip over this and I'm just going to go straight to, I'm just going to, okay, we'll go through linear regression and then we'll try at least get one or two more in. So multiple linear regression. So let's say, so multiple linear regression, that is just in the GLM world is a GLM with a Gaussian distribution and an identity link. Let's assume we've got a cross-sectional survey of community blood pressure, so we've measured blood pressure, and our aim is just to describe the differences in systolic blood pressure by location of the community. So our outcomes, blood pressure in millimeters of mercury, our independent variable is location, rural, non-slum, slum. Okay, so first of all, we just do an exploration of the raw data, try and understand it, do some basic sample descriptive statistics. Certainly I'd always recommend visualizing your data. Like here we can see we've got the different locations and we've got histograms, so distribution of the blood pressures. We can kind of see there's kind of maybe 3 distinct peaks relating to the different locations. So if we want to describe those, a simple approach would be to run a linear regression with our outcome variable. So up here, so this is output from R, by the way. And as I say, in the materials afterwards, I'll put together the kind of the equivalent in Stata. But in R, we've got a model here where we've got blood pressure as the outcome, location as our independent variable, and we've got a whole load of results that get spat out. I'm not going to go through any of them apart from the model coefficients. But again, in the other materials, we can kind of talk through some of these and highlight whether they're of much use. They're generally not actually particularly useful. So we've got our coefficients, we've got our intercept. So if you look here, we've got location slum and location non-slum. So R is trying here to kind of illustrate which is the reference category and which are the comparisons. So this is the way it lays it out. So it's saying we've got an intercept, which is going to be the mean for rural, because we've got slum here and non-slum here. So we know that rural is being taken as the intercept. So the mean blood pressure in rural is going to be this. And then the difference to being in a slum is an extra 2.6 millimeters of mercury. And the difference from rural to non-slum is an extra 5.2 in terms of the mean. And you can see that reflected up here just in the raw data. So in the raw data, the mean for rural was 119, for slum it was 122, and for non-slum it was 125. So obviously we've got our coefficients, and how do we make inferences to the wider population? Well, we use our confidence intervals. So this tells us the likely value of the likely true value of the coefficients in the wider population. Again, we can come, in kind of offline materials, can go into a bit more detail about how you would interpret that and the meaning of the confidence intervals. And then we can also use marginal effects on our model to look at these predictions. So we can get our mean blood pressure values for the 3 locations. So, again, this is just going to reflect the mean in the raw data, so it's not actually that useful in this situation, but we'll see how it becomes much more useful in the linear regression setup. And then we can get the comparisons. So we can get non-slum minus rural, non-slum minus slum, slum minus rural. So we've got all possible comparisons. We can also flip those around if we want. And these are the difference in the mean blood pressure between the different locations. Okay. Right. I want to, as time is really tight, there are some different linear regression examples here, but I want to skip on to logistic regression. So this would be a generalized linear model with a Bernoulli or binomial distribution and a logic link. Let's assume we've got another cross-sectional survey, and now we're looking at facility service readiness. And our aim is to describe differences in service readiness by location. So our outcome now is the facility ready or not ready for some given service? Maybe it's diabetes, maybe it's hypertension, whatever it is we're looking at. We've got a way of measuring whether it's ready or not. So it's binary, and our independent variable is location. So we're just thinking in terms of one independent variable here, and we want to understand how service readiness varies by location. So again, we do a data exploration, explore the data, and then we fit the model. And now this is a logistic regression. So we've got our readiness is our outcome variable, our location is our independent variable, and we've got, again, coefficients for our intercept. And then because it's a categorical variable, it's got dummy coding. And so we've got comparisons between slum to rural and non-slum to rural. But as this is a logistic regression, the kind of initial output, the coefficients are on the logit scale. So, for example, this is saying that in the rural areas, the logit, which is the log of the odds of being ready, is minus 0.007. Now, I'd certainly look at that and it doesn't really mean anything to me. So the first approach that you typically, I'm going to have to skip over this really because we're quite tight on time. The first approach that you will usually find is that people will then transform those coefficients by exponentiating them, which basically just undoes the log part of the logit transformation. And then you can interpret them in terms of odds ratios. So now we've got our intercept in terms of the odds, and then we've got odds ratios for urban slum and urban non-slum. So this is saying that individuals so saying the odds ratio for urban slum compared to rural is 0.65. And so that's on a ratio scale. So it's saying how many times the odds change for urban slum versus rural. Again, you might find odds ratios not, super intuitive still, which, I'd agree with. So this then illustrates how we can use marginal effects to kind of then go one step further and get back to the actual probability scale and look at differences. So we can use marginal effects to take our logistic regression model, and instead of looking at the associations on a logit scale or on an odds ratio scale, we can actually look at them in terms of the probability scale, which hopefully is more meaningful. And so we can look at the mean probability or the mean proportion of the observations in the rural area. So it's saying about 50% of rural facilities are ready, about 82% in non-slum areas are ready, and about 40% in slum areas are ready. And then generally what's going to be, the kind of key result for your research question is, what are the differences between these groups? And now, thanks to the marginal effects being able to contrast the differences on the probability scale, we can think in terms of differences in probabilities or equivalently differences in proportions or percentages. So, for example, here we've got urban non-slum minus rural. So it's saying, what is the difference in readiness in non-slum facilities minus rural facilities? And it's saying it's plus 0.3. So you can see here, if we go urban non-slum, that's 82% of urban non-slum facilities are ready, and 49 or 50% of rural facilities are ready. So it's saying we're taking the urban non-slum and we're subtracting the rural one, and we're ending up with 0.3. So it's saying that urban non-slum, so at 80%, is about 32 percentage points more ready than the rural facility. And so then hopefully that is, a bit more intuitive. Okay, so sorry that we've kind of run a bit out of time. We did lose a bit of time at the start, but equally, I think as I was a bit worried, there was a bit too much to get through. I just wanted to finish, I guess, then with one more that we can look through quickly, which will be account regression. And then at least hopefully we've covered kind of the three core models, because I would say that, a good, probably 95% of outcomes are probably going to be usefully modeled either with a multiple, a linear regression, if you've got a continuous variable, or a logistic regression, if you've got a binary variable, or if they're counts or rates with, as we'll look at now, a Poisson or a related model. So kind of count regression in the general sense would be a generalized linear model, maybe with a Poisson distribution and a log link, but this is actually, you rarely find that that's ideal because it doesn't model the variance properly. So two other options are quasi-Poisson, which basically makes a kind of ad hoc adjustment to the Poisson, or negative binomial, which uses a slightly different distribution. But the good thing is that for any of these three approaches, the interpretation of the mean model, so the interpretation of the relationships between the independent variables and the count, the expected count, doesn't change. So it's, once you've kind of understood how to interpret one of these models in terms of the relationships, you can understand all of them. The different types of model are mainly to make sure that you model the variance correctly, which will affect the confidence intervals, but it won't affect the point estimates. So final little example, let's say we've got a cross-sectional survey of facility stockouts, and we want to understand the relationship between, again, location and stockouts. So how do stockouts vary by facility location? So our outcome is stockouts over a 1 month period, and our independent variable is location, rural, non-slum or slum. So when we run our model, initially this is going to be on the log count scale, because any of the count models use a log link. So again, differences in log counts, it's not necessarily that intuitive. Normally we want to think in terms of, differences in counts or ratios of counts. So the first thing we can do is we can transform these coefficients, again, by exponentiating them, which undoes the log part. And then we get to count ratios. I'm not going to kind of go through these one by one, but broadly speaking, we can look at the ratio of the expected count between the different locations. So, for example, in slum areas, the ratio is 2. So it's saying in slum areas compared to rural areas, the expected count is going to be twice in slum areas compared to rural areas. And then again, we can use marginal effects if we want to shift back to a different scale rather than a ratio scale. So we can use the marginal effects on the model. We can get our expected count of the, expected number of stockouts in the different locations, and we can get the differences between them. So again, for example, here we've got in non-slum facilities minus rural facilities, we've got -1. So if we look here, we've got non-slum, the expected mean number of stockouts is 3.7, and in rural areas it's 4.7. So, when we subtract, when we have 3.7, we take away 4.7, we get about -1. So it's telling us that in rural areas, the number of stockouts is about, 1 stockout per month lower on average than in non-slum areas. The number of stockouts is about 1 stockout less than you'd expect in a rural area. Okay, so you can go through these slides, and as I say, there's kind of a lot of other examples here which we don't have time to go through now, like looking at a quasi-Poisson model with a numerical outcome. So then we're looking at a trend. So you can go through those, and then, as I say, for the other materials, I'll provide code to kind of look at these, run these models in R and Stata with hopefully some useful explanations so that you can kind of interpret what you're looking at. So hopefully that'll be useful. Sorry we've been a bit cramped for time and haven't been able to get through what I wanted. Final thing just to finish on is, I guess, basically just a heads up that, there's lots and lots of other stuff that not even touched on here really, or at least have touched on but haven't gone into any detail. So things like checking the assumptions of the models, that they're all valid, model diagnostics, collinearity, that kind of stuff. So basically making sure that, your results are reasonably trustworthy just from the modeling perspective. As I said, non-independent observations due to longitudinal data like repeated measures or due to clustering is super common. So how do we deal with that? So there are different ways we can deal with that. And I'll go into some of those in the offline code. Similarly, complex survey sampling features. If you've used a survey with clustering or strata or unequal weighting, you need to account for that. Again, we can have a look at how you go about doing that with some example offline code if that's useful. Missing data, that's a vast thorny topic, and sensitivity analyses. So I think it's fair to say by far the norm in the literature, is when you read a quantitative study, you'll often just see there's kind of one model and like that's it. But really what we should be doing, much better practice is to kind of, run additional models, maybe with, varying our assumptions in terms of, maybe that's what variables we include in the model, independent variables. Maybe it is using, different distributions and seeing how the results change and, seeing how robust our results are to those different